Hello everybody, welcome to another video. In this video we're going to be covering section 3.1, which is entitled Complex Numbers. In chapter 3, overall what we're going to be doing is we're going to be studying two types of functions called polynomial functions and rational functions. Before we do that, we're going to start with a little detour in this section and talk about complex numbers. And I have a motivating question here, and that is, are there any real number solutions to the equation x squared plus 9 equals 0? Okay. So what we're going to do is we're going to go ahead and try and solve this to find the solutions x, so that x squared plus 9 equals 0. Now there are two ways to do this. One is, since x squared plus 9 does not have an x term, we can simply isolate x to find our solutions. Okay, so I start with the equation x squared plus 9 equals 0, and we'll go ahead and, of course, try to get x by itself by a starting of subtracting 9 on both sides to cancel that 9. That's going to give us x squared equals negative 9. Now, right away, I basically know there's no real number solutions to this equation because there are no real numbers that square to a negative. Right? Any positive number squared or negative number squared will result in a positive number, but let's just pretend we can do this anyways. So what we'll do is we'll go ahead and take the square root on both sides. And of course, the square root of x squared is x, but either positive or negative square root of negative 9 will square to negative 9. Okay, so there are two solutions, but x equals the square root of negative 9 and minus the square root of negative 9 are not real numbers. Okay. We cannot take the square root of negative 9. There is no number that multiplied by itself equals negative 9 or minus negative 9. Okay, so there are no real numbers. There are no real numbers that square to negative 9. Okay, so these are the solutions to the equation. It's just the square root of negative 9 and minus the square root of negative 9 are not real numbers. Okay, so note is that what we're going to be studying, complex numbers, arise as solutions to what are called polynomial equations. Okay, so here we have a quadratic equation, x squared plus 9 equals 0, but there are polynomials where x is raised to even higher powers, like x cubed, x to the fourth, that may or may not, they might have some real number solutions, but they may also have complex number solutions, or what are called complex numbers. Okay, so that is one way that complex numbers will arise. So let's talk about what complex numbers are. Now, complex numbers arise in various applications, such as electrical engineering and other places, but for us, they're just going to arise as solutions to polynomial equations. Some polynomial equations will only have real number solutions, or only complex solutions, and actually some polynomial equations will have both real number and complex solutions. So we'll start here with the definition of a complex number. Okay. Now, let me give you some background here below the definition before I revisit it. Okay, so when you build the real numbers, what you really want to do is you want to start thinking of, and I'm going to create a box here. Okay, so in this box, I want you to imagine that we have all the possible real numbers, and within the real numbers, you would maybe start with what are called integers, So those would be your whole numbers, like -2, 3, 10, 100. So anything that's a whole number, whether it's positive or negative. And slightly larger set of numbers would be that contains the integers would be rational numbers. Now these would be like your fractions, like 3/2, -5/2. So anything that can be written as a fraction is a rational number. And it turns out that whole numbers are also rational because the number 2 can be written as the fraction 2 divided by 1. And then you also have what are called irrational numbers. And some examples there would be like square root of 2, pi, square root of 7. Anything that cannot be expressed as a fraction or an integer. Okay. Now, real numbers are also part of a larger system of numbers called complex numbers. Okay. So we have a larger set of numbers called the complex numbers, and contained in that set of complex numbers would be the real numbers, whether they're rational or irrational. Okay, so rational numbers expand integers to fractions, and then the real numbers are completed by also considering irrational numbers, and then complex numbers is an even larger set of numbers that contains the real numbers. Okay, so that's one way to think about this. Okay, is that complex numbers are just an expansion of the real numbers into a larger set of values. Now, a complex number is any number that can be written in the form a plus bi. And we'll talk about this later, but the number I turns out to be the square root of -1. Okay, so any complex number can be written in the form a plus bi, where we call a the real part of the complex number, and the multiple of I, bi, is what we call the imaginary part of the complex number. Okay. If b is equal to 0, then a plus bi just ends up being a real number. And finally, if a is 0 and b is not 0, the complex number is what's called imaginary. Okay, so a complex number is one that has a real and an imaginary part. If the imaginary part is 0, then a complex number is a real number, just like we're used to working with. And if the real part, a, is equal to 0 and b is non-zero, the complex number is called an imaginary number. And we said an imaginary number is just an even root of a negative number. And that's because I is equal to the square root of -1. And we saw in our motivating question that these square roots of negative numbers arise as solutions to certain equations. Okay, like x squared plus 9 equals 0. So we're just going to get used to the terminology here in our first example. So if I was being asked, what are the real and imaginary parts of the complex number 2 minus 3i? So 2 minus 3i, right, is supposed to be this complex number a plus bi. And I'll rewrite it here as 2 plus -3i. Okay, so the real part is equal to +2, and the imaginary part is equal to -3i. Okay, and that's again where I is equal to the square root of -1. Now, in this video, we're going to do many things. We're going to learn how to rewrite square roots of negative numbers in terms of I. We are going to learn how to add and subtract complex numbers, and we're going to learn how to multiply and divide complex numbers. And then, given a function, we're actually going to find the output of a function where we use complex numbers as their input. We're also going to learn how to visualize complex numbers by viewing them in what's called the complex plane. And I don't want to get too far ahead of myself. All of that is coming shortly. Okay, so now we're going to talk about writing square roots of negative numbers in what's called their standard form. Okay, so at the top we have this how-to. So say I want to rewrite the square root of minus a. Step 1 is to begin by writing it as the square root of a times the square root of negative 1. And we know that square root of negative 1 equals I. So number 2 is to rewrite or express square root of negative 1 as I. And then step 3 is just to simplify by writing square root of a times I in as simple a form as possible. So we'll do a couple examples here. So we'll start with doing the square root of negative 16. Now you can think of that as the square root of 16 times negative 1. And then the square root of a product of two numbers is the product of their square roots. So this can be written as square root of 16 times the square root of negative 1. And the square root of 16 is really just looking for a number that multiplied by itself equals 16, which is 4. And then we rewrite the square root of negative 1 as I. So the square root of negative 16 reduces to 4i. Now we're going to do the square root of minus 32. And again, we'll think of that as the square root of 32 times negative 1. And we can rewrite that by taking the square root of 32 times the square root of minus 1. Okay. Now we're going to simplify this. We're going to express the square root of negative 1 as I. So this becomes the square root of 32 times I. And then we can further reduce this by simplifying the square root of 32. Okay. Now we're going to start by rewriting the square root of 32 as 16 times 2 and then times I outside of the square root. So if you're trying to simplify the square root of a number, the best thing to do is to rewrite it as the largest square divisor you can think of. So in this case, 16 is what's called a perfect square because it's 4 squared. Okay. So that's the largest perfect square divisor of 32. So I went with 16 times 2. And finally here now, we'll take the square root of 16, which is 4, times the square root of 2 times I. So the square root of negative 32 can be written as 4 root 2 times I. Now, next thing we're going to do is we're going to talk about plotting complex numbers in what's called the complex plane. So, note at the top, real numbers can be expressed visually by plotting them on a number line, but since complex numbers have two parts, real and imaginary, they must be plotted in what's called the complex plane, right? So, if I had the number x equals 3, okay, that's a real number. We can visualize the x-axis as a number line, and maybe we'll put 0 in the middle. We have negative 1, negative 2, negative 3 going to the left. We have 1, 2, 3, 4 going to the right. But I can easily visualize x equals 3 on that number line at the location of 3. Okay. But again, complex numbers have two parts, real and imaginary, so a one-dimensional number line is not going to work to visualize them. Now, the complex plane is going to be similar to the xy coordinate plane. They're going to have a vertical and horizontal axis, but my second note or warning is the complex plane and the xy coordinate plane are not the same. They are very different. The complex plane is for plotting complex numbers, and the xy coordinate plane is for plotting points for relations or functions between real numbers. Okay, so how to, in the box here, is given a complex number, we're going to represent its components on the complex plane. So step 1 is to determine the real part and the imaginary part of the complex number. We're going to move along the horizontal axis to find the real part, and then we're going to move vertically parallel to the vertical axis to show the imaginary part of the number. And then we're really just going to essentially view the real part and the imaginary part as the x and y coordinates of a point. So, moving into an example, if I had the complex number 2 minus 3i and I wanted to plot it in the complex plane, what we'll do is we will, just like the xy coordinate plane, create a horizontal and a vertical axis, although the horizontal axis is called the real axis. The vertical axis is called the imaginary axis. Okay, so with the number 2 minus 3i, the real part, as we did in our example above, the real part is equal to 2, and the imaginary part is equal to negative 3i. So what we're going to do is we're going to move along the real axis 2 units to the right, and we're going to move down the imaginary axis 3 units. And we can now just plot that imaginary number in the complex plane by going 2 units to the right and 3 units down. And there would be how we're going to visualize our complex number 2 minus 3i. So basically, you can just think of the real part and the imaginary part as horizontal and vertical coordinates, just like if you were plotting a point that was on the graph of a function. You'd have your x coordinate and your y coordinate. Okay, so what else are we going to do? So we'll first talk now about complex arithmetic, where we're going to be adding and subtracting complex numbers. And to add two complex numbers, a plus bi and c plus di together, what we're going to do is we are certainly just going to take the real parts a and c and add them together to get the real part of the result, a plus c. And then we'll also identify the imaginary parts b and d. And when you add bi to di, you're going to get b plus d times I. Okay. Now, if you were going to do subtraction of complex numbers, okay, so you would first identify the real parts a and c that I have highlighted in orange. Okay, and obviously we're subtracting these two complex numbers, so the real part becomes a minus c. Okay, and then you can identify the imaginary parts, bi and di, and essentially what you're going to do is bi minus di, but the I can be factored out, and the result becomes b minus d times I. So looking at the bottom here, again, if you're going to add two complex numbers, you can identify the real and imaginary parts of each number. And depending on if we're doing addition or subtraction, we're going to add or subtract the real parts, and then we're going to add or subtract the imaginary parts. So we'll go ahead and do this example here on the bottom. So I want to add or subtract here. I'm just going to do an example of subtraction. Now, there's another way to think about doing this, because I'm going to take the complex number 3 plus 4i and subtract the complex number negative 2 plus 3i. And the good news is you can just kind of treat I like a variable. So the first thing we can do is distribute the minus sign. And what we would get here is 3 plus 4i. Now minus negative 2 becomes a plus 2. And subtracting the 3i is going to become a minus 3i. Okay, so that the subtraction is just going to turn into an addition. 3 plus 4i plus 2 minus 3i. And just like above, we're going to add the real parts. So the real part of 3 plus 4i is 3. The real part of 2 minus 3i is 2. And we're going to simply add them together. Plus, in my second set of parentheses, we're going to take the real part of the first number, 4i, and we're going to add negative 3i, which just becomes subtraction, 4i minus 3i. And then finally, the parentheses can be dropped. 3 plus 2 is going to give us 5, plus 4i minus 3i. If I have 4 things and I take away 3 of them, then of course you're just going to be left with a single I. Okay, so those two complex numbers being subtracted gives us a result of 5 plus I. So the addition and subtraction isn't too bad. And again, essentially you're treating I as a variable, so the same rules of combining like terms and factoring will still apply. But there's a few caveats, because now we're going to do multiplication and division, and there's one added piece that's going to help us simplify when we're doing multiplications and divisions. So let's start with multiplication. All right, so now let's talk about the multiplying of complex numbers. Now, given two complex numbers, when we're going to multiply to find the product, number one, we're going to use the distributive property if we're only multiplying a complex number by a real number. But if we're multiplying two complex numbers with real and imaginary part, we're just going to use the FOIL method, just like if we were going to multiply something like x plus 2 times, say, x minus 5. Okay, so again, this is not too crazy. If I was going to take the real number negative 4 and multiply by the complex number 3 minus 5 halves I, this is the case where we are going to be using the distributive property. As you can see, I have highlighted in step 1. Okay. And the negative 4 is going to be multiplied by 3 and by the minus 5 halves I. Okay, now negative 4 times 3 is going to give us a minus 12. And negative 4i times minus 5 halves I, multiplying a negative times a negative is going to switch that sign to a positive. And then 4 times 5 is going to give us a 20. We still have the divided by 2, and we still have the I. And then, of course, we still have the negative 12 out front. 20 over 2 can be reduced to 10. So when all is said and done, we're going to get negative 12 plus 10i. Okay, so again, it's no different than multiplying, say, 5 times x plus 2. We just distribute the real number to both terms inside the parentheses and simplify. For part B, now there's one thing I want to remind you. This time we're multiplying two complex numbers with real and imaginary part. So this time, in step 1, we're going to be using the FOIL method. But let's talk about one thing. At some point in this multiplication, we're going to have to multiply I times I. So what is I times I? Well, of course, just like x times x, that's going to be I squared. And we know that I is the square root of negative 1, and we're going to be squaring that square root. And squaring a square root, they cancel each other. So it turns out that I squared, or I times I, just ends up being minus 1. Okay, so now let's go ahead and multiply these two complex numbers, 3 minus 2i and 4 plus I. And again, we're just going to be using that FOIL method. So 3 is going to multiply by both 4 and I. And the negative 2i is going to also multiply by 4 and I. Okay, so multiplying 3 by both terms on the right, 3 times 4 is 12. 3 times I is 3i. And then now multiplying negative 2i by the 4 and the I on the right. Negative 2i times 4 is a minus 8i. And negative 2i times I would give us a minus 2i squared. Okay. Now I'll simplify a little bit. We still have the 12 out front. But the 3i minus 8i, that's just like combining like terms. 3 minus 8 is negative 5, so 3i minus 8i would give us a minus 5i. Okay. And sorry, I'm getting some notifications on my screen here. There we go. So my 3i minus 8i gave me that minus 5i. And then we still have minus 2 times I squared, but we now know that I squared is negative 1. So now I have 12 minus 5i, and then on the back end we have negative 2 times minus 1. Negative times a negative is going to change that to a positive, and 2 times 1 is 2. And now we just collect like terms. 12 plus the 2 on the end is 14, and we still have the minus 5i. So the result of that product is the complex number 14 minus 5i. Okay, so that's how multiplication works. Addition and subtraction are also very similar. We're just using the same rules of algebra that we used when we were simplifying expressions with variables. You just have to remember that when you're multiplying complex numbers, we can always rewrite I squared as negative 1. All right, so now it's time to talk about dividing complex numbers. And before we're able to do that, we're going to have to learn about what is called the complex conjugate of a complex number. And turns out that whether we start with a plus bi or a minus bi, as I have highlighted, those two complex numbers would be conjugates of each other. So notice that the complex conjugate of a complex number would still have the same real part. So in this case, both the real part of each of those is a, but the sign in front of the imaginary part has changed. Okay, so again, reading that, the complex conjugate of a plus bi is a minus bi, and again, it's found by changing the sign of the imaginary part of the complex number, and the real part of the number is left unchanged. And it's interesting, it turns out, when a complex number is multiplied by its conjugate, the result is just a real number. And it's also true that when a complex number is added to its conjugate, the result is a real number. So we're going to do an example here finding conjugates, and then we're going to go ahead and dive right in and use conjugates to do complex division. So find the complex conjugates of 2 minus 3i and negative 3 halves I. So, I had my highlighter still on. The complex conjugate of 2 minus 3i is just 2 plus 3i. Okay, so again, both of those are conjugates of each other just by changing the sign on the imaginary part. And the complex conjugate of negative 3 halves I, which you could think of as 0 minus 3 halves I, is 0 plus 3 halves I, which can just simply be written as 3 halves I. So if a complex number only has imaginary part, like in this case, negative 3 halves I, then we just simply change the sign, and the conjugate would be 3 halves I. Okay. All right, so by the way, the complex conjugate of a real number is still the same real number. So the conjugate's really only interesting if the complex number has an imaginary part. Now, I was just saying we're going to use complex conjugates to do division problems. So how are we going to do this? Now, ultimately, the goal is, I'll write this down below, we're going to divide 3 plus 5i by 2 minus 4i. And remember that, it doesn't usually say this, but we're going to write the result. Having a hard time writing today, folks. We're going to write the result in the form a plus bi. Okay, now step number 1 is to write the division problem as a fraction. Okay, so we're going to be dividing 3 plus 5i by 2 minus 4i, and somehow there's a way to write this in just the standard form a plus bi. So what we're going to want to do, step 2, is to determine the complex conjugate of the denominator, and then after that, we're going to multiply both the numerator and denominator of the fraction by the complex conjugate of the denominator. Okay, so what's that going to look like is now we're going to multiply by a fraction here. In the denominator, we have 2 minus 4i, so we're going to multiply top and bottom by the complex conjugate. Okay, and what we get here in the numerator, we're going to have 3 plus 5i times 2 plus 4i. And in the denominator, we're going to have 2 minus 4i times 2 plus 4i. Okay. Now, we're going to FOIL on top and bottom. Okay, so I'm going to skip the part where I draw the arrows. But in the numerator, when we FOIL, 3 times 2 is 6. 3 plus 4i is 12i. 5i times 2 is 10i. And 5i times 4i is going to be a positive 20i squared. In the denominator, 2 times 2 is 4. 2 times 4i is 8i. And then now negative 4i times 2 is a minus 8i. And negative 4i times positive 4i would be a minus 16i squared. Now, in the denominator, what you're going to notice is that 8i and minus 8i are going to cancel. And now we're left with, well, in the numerator, we might as well simplify that a little bit. We're going to leave 6 in the front. 12i and 10i are going to add to 22i. And remember, I squared is negative 1 times 20 would give me a minus 20. Okay, so remember, I squared is negative 1. Now in the bottom, we're left with 4 minus 16i squared. Now, I squared is negative 1 times negative 16 is going to change negative 16i squared to a positive 16. In the numerator, we're going to simplify. 6 minus 20 is negative 14, and we still have the 22i. And in the denominator, we have a 4 plus 16, which is 20. And now we're going to split up the fraction. So in the numerator, we can take negative 14 times 20, plus we also have the 22 over 20 times I. And I've kind of screwed up here. I didn't leave myself enough room to simplify, but I'm going to come to the left in black. So what we have so far is 3 plus 5i over 2 minus 4i is equal to minus 14 twentieths plus 22 over 20 times I. And reducing that down, negative 14 over 20, if you divide top and bottom by 2, will give you a minus 7/10, plus dividing 22 over 20 by 2 on top and bottom is going to give us 11/10 times I. And there is the division of our complex numbers written in that standard form. The real part is negative 7/10, and the imaginary part is 11/10 I. Okay, so there's our process for doing that. Now, here's one thing that I want to point out to you real quick before moving on. So we've done that problem, but I do want to give you guys a note. So remember, what we just did was we were dividing by 2 minus 4i, and we had to multiply by its conjugate at some point. And we ended up getting 4 plus 16, which you may notice is 2 squared plus 4 squared. Okay, so if you think of the number 2 minus 4i as our a plus bi, okay, a is equal to 2, and b is equal to minus 4. Okay. And in general, I'll tell you the formula. If you take a complex number times its conjugate, a plus b times a minus bi, it ends up being true. That's just a squared plus b squared. Okay. So actually just above here, that really should have been a negative 4 squared. So a was 2 and b was negative 4. So there's just a really easy way to multiply complex conjugates together to get your result. So I back up a little bit here. I could have skipped, and I'll box this in green. When I multiplied in the denominator 2 minus I, 4i times 2 plus 4i, I could have skipped straight to 4 plus 16 because 2 squared is 4 and 4 squared is 16. 4 plus 16 gave me 20. So I kind of, rather than using the FOIL method, I could have just used the formula to do a shortcut. Okay, so a couple things left that we're going to do, and that is, what if we take a function that we usually take real number inputs and we use real number inputs to achieve real number outputs, and what if we actually plugged complex numbers in for our inputs and simplified? Okay, and then the last thing we're going to do here is tackle powers of I. Okay, so example 8, f of x is x squared minus 2x plus 7. So what we're going to do here is we're going to go ahead and, rather than plugging in a real number or just a variable, we're going to evaluate a function at that complex number. Okay, so f of 2 plus I, f is the function that starts by taking the input and squaring it, then subtracting 2 and multiplying by the input, and then adding 7. Okay. Now, a couple things we're going to do here in the first step. Of course, we can distribute negative 2 to the 2 plus I. Okay. And we'll rewrite this once. Okay. Now, the 2 plus I squared, anything squared is just multiplying by itself. After distributing the negative 2 to 2 plus I, we're going to get a minus 4 minus 2i, and then we still have the plus 7 on the back. Okay, now we know that we're going to take our 2 plus 2i and we're going to FOIL that out. So ultimately, notice that, taking a quadratic function and plugging in a complex number really is just practicing doing some multiplication of complex numbers. Okay, so here's what we have now. F of 2 plus I. Well, when we FOIL, what we're going to get, 2 times 2 is 4. 2 times I is 2i, plus, and then we're going to take, on the bottom set of arrows, I times 2 is another 2i, and then I times I is going to give us an I squared. We still have a minus 4 minus a 2i and a plus 7 at the end. Now there's a little bit of cancellation this time. You'll notice that one of the positive 2i's is going to cancel with one of the minus 2i's, and one of the positive 4's is going to cancel with one of the minus 4's. Okay, so now our function value, f of 2i, is going to be, well, I'm going to rearrange these terms. I'm going to put the 7 in the front. I'm going to leave the I squared in the middle. And I'm going to put the 2i on the back. And we know that I squared is negative 1. So 7 plus I squared is 7 minus 1, which is going to give us 6. And then we still have the 2i. So again, this I squared right here just became negative 1. 7 minus 1 is 6. So if we allow our quadratic function to have complex number inputs, the resulting output for the input of 2 plus I is 6 plus 2i. Okay. Excuse me for clearing my throat there. Now we're going to also find g of 2 plus I. And g is the function that takes its input and does 2 plus that input, so 2 plus I. And in the denominator, we take the input, in this case 2 plus I, and we add 5. Now the parentheses aren't really necessary. I'm just showing you guys that my input of 2 plus I, that's how it shows up in the numerator and the denominator. Now 2 plus I, 2 plus 2 is 4. Basically, you can just drop the parentheses since we're doing addition. And in the bottom, 2 plus I plus 5 just becomes 7 plus I. Now, I said evaluate and simplify. So since we'd always like to write our complex number in the form a plus bi. So remember, our strategy is to multiply by both the conjugate of the denominator on top and bottom. So we're going to do 4 plus I times 7 minus I, and we're going to take 7 plus I times 7 minus I. Now the shortcut in the bottom is going to be just doing 7 times 7 is 49. The imaginary part of 7 plus I is 1, so we're also going to add 1 squared, which is also 1. So that's my shortcut. If you forget how to do that, you can always FOIL. Now, foiling out the numerator, 4 times 7 is 28. 4 times minus I is minus 4I. I times 7 is a plus 7I. And I times negative I would give us a minus I squared. Okay, remember I squared is negative 1. So after rewriting I squared as negative 1, and we're taking the negative of that, you guys can verify that 28 minus I squared becomes 29, and minus 4I plus 7I is going to become a 3I, and in the bottom, 49 plus 1 is going to give us 50, and then splitting up fractions is going to give us 29 over 50 plus 3 over 50 times I, and there is our complex number output, where we use the function g of x to input the number 2 plus I. Okay, now I have one more example to do, trying to keep the video as short as I can. Make sure you're taking some breaks, just some mental breaks every once in a while during the video. Okay, especially if you're kind of having trouble following along or getting a little tired or burnt out. Okay, so what we're going to talk about now is powers of I. Now we're going to start by remembering that I is equal to the square root of negative 1. We saw that I squared was the square root of negative 1 squared, and we get negative 1. I cubed is going to be I squared times I. Okay, and we know I squared is negative 1, so we get minus I. And I to the fourth is, well, I guess we could do this by rewriting I to the fourth as I squared times I squared, because when you multiply the same base, you add the exponents, and 2 plus 2 gives you 4. We know that I squared is negative 1, so I squared times I squared becomes negative 1 times negative 1, and I get positive 1. Now, interestingly, what if I start looking at I to the fifth? Well, that's I to the fourth times I, and we just did I to the fourth and it was 1. Turns out I to the fifth is I. I to the sixth is I to the fourth times I squared. I to the fourth is 1. I to the fourth is negative 1, so I just get minus 1. And we can keep doing this process, but it turns out I to the seventh is minus I, and I to the eighth is positive 1. So I to the n equals one of 4 possibilities. I to a power is either I, negative 1, minus I, or positive 1, depending on the power of n. Because even if I did I to the 9th, I to the 10th, I to the 11th, and I to the 12th, those values are just going to keep repeating themselves. So one of the interesting things about powers of I, again, is there's only 4 possibilities, plus or minus I, or plus or minus 1. Okay, now there is a nice way to do powers of I without really, doing a whole lot of work. And I really just kind of base everything I'm going to do on I to the fourth equaling 1. Okay, so real quick before I do an example, like if I was to take something like I to the 36th, 36 is divisible by 4, so this could be rewritten as I to the fourth to the 9th power, right? 4 times 9 is 36, and I to the fourth is 1. Okay, so I get 1 to the 9th, and 1 to any power is 1. And it's actually true that I to the n always equals 1 if n is divisible by 4. Okay. So now on the bottom, if I'm going to do something like I to the 37th, what I always do is I split it up as a product of two powers of I, where one power is the largest number I can think of that's divisible by 4, and since I'm doing I to the 36th times a power of I, I'm going to put it in, but this I to the 37th could be written as I to the 36th times I to the first power. But of course, there's really no need to write I to the first. This can just be thought of as I to the 36 times I. But as I just showed you above, since 36 is divisible by 4, I to the 36 is just equal to 1. And then, of course, we have times I, and 1 times I is I. Okay, so I to the 37th is just I. And we can do the same thing with I to the 43rd. I'm going to split it up as a product of two powers of I, where the power on the power on my first I is the largest number I can think of that's divisible by 4 and less than 43. Okay, so I'm going to do I to the 40th power, which means that I have 3 powers of I remaining, so I'd have to multiply that by I cubed to get I to the 43rd. And 40 is divisible by 4, so I to the 40th just equals positive 1 times I cubed, and 1 times I cubed is just I cubed, and I believe that we just saw that I cubed was equal to minus I. So again, you really, and I'll write it on the bottom, you really only need to remember that I is I squared is negative 1, I cubed is I, minus I, sorry, and I to the 4th is equal to 1. Okay, so if you know the first 4 powers of I, you can actually find any power of I by always reducing the power to the largest number that's divisible by 40 that you can think of, and finding the leftover power and simplifying from there. Okay, so that's what I'm going to leave you guys with. Thanks for having the patience to make it through the video. If you have questions, let me know. Otherwise, take care. Until next time, and we'll see you soon. Thanks, everyone.